Hello, I'm Zongqi Cao from Northwestern Polytechnical University. I'm glad to present you our work, a new comprehensive benchmark for semi-supervised video anomaly detection and anticipation. For a quick overview, firstly, we propose a new large-scale dataset named NWPU Campus. It is currently the largest dataset for semi-supervised video anomaly detection, the only one considering scene-dependent anomalies, and the first one proposed for video anomaly anticipation. Secondly, we propose a novel forward-backward scene conditioned autoencoder, which can detect scene-dependent anomalies and anticipate the anomalies in the future by the consistency between the historical observations and backward predictions. Our proposed method achieves leading performance on both video anomaly detection and anticipation. VAD aims to detect unexpected abnormal events in videos. For the semi-supervised VAD, there are only normal events in the training set. The model trained only on the normal events needs to distinguish anomalous events from normal in the testing phase. Semi-supervised VAD has been studied for years. Here we show training and testing examples from 4 typical datasets. As we investigate, most of the existing datasets only focus on appearance and short-term motion anomalies. Researchers overlook an important type of anomaly, that is the scene-dependent anomaly, which refers to that an event can be normal in one scene but abnormal in another. Besides VAD, we argue that anticipating the occurrence of abnormal events for the future is also of great significance to prevent accidents. However, most of the existing VAD datasets are not suitable for video anomaly anticipation since a considerable portion of anomalies are intrusions of unexpected objects. To address these issues, we propose a new large-scale dataset NWPU Campus. The statistics of the dataset are shown on the left side. The proposed dataset contains 43 scenes, 16 hours of videos, and 28 classes of abnormal events with scene-dependent anomalies. Several samples are shown in the figure. The samples in the first column are normal events, while the others are different classes of anomalous events. To explain the scene-dependent anomaly, an example is shown in the blue box. Moreover, our dataset is also suitable for anomaly anticipation for the reason that we take into account the complete process of the events in the data collection phase, so that the occurrence of abnormal events is predictable. We make a quantitative comparison between the NWPU Campus and the other datasets, as shown in the table. Our dataset mainly has the following 3 advantages. First, it is the largest VAD dataset to date, with the longest duration, the largest number of classes of anomalies and scenes. Second, it is the only VAD dataset containing scene-dependent anomalies. Third, it is the first dataset proposed for semi-supervised video anomaly anticipation. In addition, we propose a new formulation of video anomaly anticipation. Instead of predicting the exact moment when an abnormal event happens, we define VAA to anticipate whether an anomaly will occur in a future period of time, since it is not necessary to estimate the exact boundary between anomaly and normality in practice, which is a robust setup for the cases where boundaries are uncertain. We propose a novel method to detect and anticipate anomalous events simultaneously, and it can cope with scene-dependent anomalies. Our method consists of a forward and a backward frame prediction network. Each one has the same U-Net architecture with conditional VAEs that take the scene image as the input. First, the past observed frames are fed into the forward network to output the predicted current and future frames. We can use the error between the predicted current frame and its corresponding ground truth to detect anomalies. Then the predicted future frames are fed into the backward network to predict the historical frames. We use the error between the historical observations and backward predictions to anticipate the anomalies in the future frames, which have not been observed. In the forward and backward networks, there are conditional VAEs on the shortcuts of the UNet. A conditional VAE takes the encoding of the corresponding scene image as the condition to reconstruct the input frame feature maps. As a result, the error between the output frames and the ground truth is also controlled by the scene and thereby detects scene-dependent anomalies. The comparison for VAD between our method and other existing methods on 4 datasets shows that our method achieves leading performance. Moreover, since the proposed NWPU campus dataset contains various types of anomalies, it is more challenging than other datasets and the existing methods cannot perform well. To study scene-dependent anomalies, we experiment on the proposed NWPU campus dataset and the Shanghai Tech SD dataset that reorganized by us using the samples from Shanghai Tech dataset. Our proposed scene-conditioned VAE has a significant improvement on both datasets and also has a higher score gap than other methods, thus can better distinguish anomaly from normality. For VAA, we conduct experiments on the NWPU campus with different anticipation times. It can be seen that our forward-backward prediction method is more effective than the forward-only method. However, there is still much room for improvement compared with the performance of humans. Finally, we summarize our work as follows. First, we propose a large-scale and challenging dataset NWPU campus for semi-supervised video anomaly detection and anticipation. Second, we propose a forward-backward scene-conditioned model for VAD and VAA, as well as handling scene-dependent anomalies. Third, the proposed model achieves leading performance on VAD and VAA tasks. In the future, our research will focus not only on the short-term video anomaly anticipation, but also on long-term anticipation. Our dataset and code have been released. That's all. Thank you for listening.